So we're going to go ahead and get started on our first lesson in the calculus sections today. And it's going to be kind of an easy intro because we're going to take a look at some pre-calculus statements that you probably have seen last year. And we're going to go ahead and talk about a more mathematically correct way to write those statements. What I'm going to refer to those as kind of calculus notation. So again, this is what we talked about last year, but this is how I want you to write it this year. So our first equation is given by this rational function, meaning a fraction, and you can see how the graph is listed to the right. We could probably list some characteristics about this graph, how we have a horizontal asymptote at the y value of 2, we have a vertical asymptote at the x value of 3, and it looks like we have a hole at the x value of -3. So looking at this equation, we can kind of see how some of that might make sense. Notice how +3 and -3 both make the denominator 0, meaning where the fraction is undefined. We also have a horizontal asymptote at 2 that's signified by the coefficient out front of both the numerator and the denominator. So 2 over 1 simplifies to 2. Okay, kind of those rules from last year that we will get into again this year. They also specify how the whole has a y value of 7 over 6, which kind of makes sense because notice how that's just a little bit higher than 1. One thing I do want to pay close attention to is how we can distinguish from an equation whether we have a whole or an asymptote. Some of us are probably familiar with the factoring technique, where if we were to factor the top and factor the bottom, that's going to be a really easy way for us to determine what's a whole and what's an asymptote. Notice how the x plus 3's would cancel. So we have a whole at the x value of -3, because that's what would cancel or make those factors equal to 0. And since this factor of x minus 3 did not cancel, we have a vertical asymptote at x equals 3. We're probably used to doing that from last year. Another way you can kind of check whether you have a whole or an asymptote based on the value of a graph is trying to substitute in some values. Notice how if you were to substitute in the x value of -3, your y value, if you tried to plug in -3 at the top, would be 0, and the y value at the bottom would be 0. So whenever you plug in a value and you happen to get 0 over 0, that's kind of signifying that you have a whole at that location. Kind of makes sense because if we're going to cancel out those factors, we're going to get a 0 over 0. This is what's referred to as an indeterminate form. And we'll talk a little bit more about that as the year goes on. So let's go ahead and check the other one. If we plug in x equals 3, I believe we would get a 30 up top and a 0 down below. So in this case, notice how you're getting a number over 0. That's signifying a vertical asymptote, something that doesn't cancel out from the top. So those are kind of some characteristics that we can look for to help us determine. We can go the factoring route, or maybe we can go the plugging and chugging, if you will, going that way. So let's take a look at some of these pre-calculus statements, perhaps from last year. We talked about a lot of end behavior, so we're going to see that again, but we're going to talk about how we can use proper calculus notation to help us write these statements. So as x approaches -infinity, as you approach the left-hand side of your graph, notice how the y values are approaching that horizontal asymptote of 2. Okay, this is how we wrote it last year. This year, we're going to talk about what's referred to as a limit. A limit is some type of statement signifying what you are approaching. So in order to take this statement from last year, we're going to show what it would look like using a limit notation. So how that's written is we have the limit as x approaches -infinity. Notice how it's a very similar way of writing it. We're going to say of the function f of x, that equals 2. So these are two congruent statements, if you will. They're exactly the same. It's just that they're written differently. You're going to see a lot more limit notation this year than you would this pre-calculus kind of sentence. So as we approach the f of x function all the way to the left, our height, aka the y value, is approaching 2. We can do the same thing for the right-hand side. As the right-hand side of the graph approaches infinity, notice how the y values, okay, same thing as f of x, are approaching 2. So the limit, as we go all the way to the right on this graph, we are equaling or approaching 2. It's not necessarily what you, I know this might be a little tricky with the equaling statement. This limit is just showing what you are approaching, not necessarily equaling. Okay, a limit is all about approaching. All right, let's try this one. As we approach -3 from the left, what does the graph approach? So here is our -3 location. I'm going to erase this. As we trace the left-hand side, notice how we are approaching, okay, getting closer and closer and closer to this hole. And this hole has a y value of 7/6. So again, it's not about what you're equaling there, it's about what are you approaching. Okay, what are you getting closer and closer and closer to? So how we can denote this in a limit is the limit as x approaches -3. To show this left-handed side idea, we're going to put a little minus sign in the exponent spot. So x is approaching -3 from the left, and f of x, the graph, is approaching the height of 7/6. Very similarly, we can do a right-sided statement. As x approaches -3 from the right, what does the graph do? Notice how we approach -3 from the right-hand side. We are getting closer and closer to that hole. So we would be approaching the same height of 7/6. The limit as x approaches -3. To show this right-sided idea, we're going to use a little plus symbol in the exponent spot. And we're approaching the same height as 7/6. So this is a key idea here. Notice how there's a hole, meaning there's no graph at the value of -3, but this limit is just showing what the graph is approaching from the left and the right-hand side. Again, it's not about what you equal, it's about what are you approaching. Let's try the next one. As we approach 3 from the left, what does the graph do? So here's the x value of 3. As we trace the left-handed side, notice how the graph continues forever downward. So the graph, meaning f of x, is approaching -infinity. So calculus-wise, using limits, as x approaches 3 from the left, the graph approaches -infinity. Let's go ahead and try the right-handed statement. As we approach the x value of 3 from the right, notice how the graph continues up forever. So the y values would be approaching +infinity. Limit notation, as x approaches 3 from the right, the graph approaches infinity. Okay, so notice how all of these limit values, the 2, the 7/6, and the infinities, those are representing y values that you are approaching, getting closer and closer and closer to. So a formal definition for us for a limit, we can say the limit as x approaches a. Okay, you can let a be whatever you want. It could be infinity, it could be a value. Okay, it's just representing whatever number you want to let x approach. So the limit as x approaches a of a function, this represents the y value, okay, the height of your graph. The y value, the graph approaches, again, not necessarily equaling, okay, the graph approaches as x gets closer and closer to a.